Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
We've previously talked about the OSI model, but did you know that it's not the only model out there? Its competition is the TCP IP model. In this video, we're going to learn about this model and see its perspective on the network. If you haven't seen the OSI video yet, now is the time to go back and check it out. As we discussed there, a model is a set of layers that describe how network hardware and software work together. The goal behind the OSI model was to allow different protocols and vendors to work together. The idea was to build protocols directly based on this model, but we don't see a lot of them today. The main reason is that the protocols from the competition, the TCP IP model, gained more popularity. The TCP IP framework was originally developed by the US Department of Defense. Later, various universities and other parties got involved. This led to rapid development, which is probably why it has been more successful than OSI in a practical sense. Now we have protocols like TCP, UDP and IP, which align directly to this framework. Another reason this framework has been so successful is that it's willing to use existing protocols, like Ethernet, if they already exist. It doesn't try to invent the wheel. Any protocol that is created as part of the framework is defined in an RFC document. Maybe you haven't come across these yet. RFC means request for comments, and is a very technical explanation of how the protocol or concept works. Some of these have been around for decades and are still used today. As these documents are available to everyone, any vendor can create hardware and software using these specifications. They'll all work together. Right now, we're looking at RFC 1122, which is the original description of the TCP IP model released way back in 1989. Now, let's take a look at the TCP IP model a little closer. Just like OSI, this model is made up of several layers. You can also see that there are two TCP IP models, which I've listed here as original and current. The original model had 4 layers and was defined in RFC 1122, which we looked at earlier. The revised model splits the bottom layer into 2 separate layers, which we'll talk about soon. The fantastic thing about the current version of the TCP IP model is that it lines up well with OSI. You can see that the OSI's session, presentation and application are all rolled into a single application layer. Personally, I prefer this. I like to think of this entire area as the application rather than trying to break it out like OSI does. I also personally think that we can break these models into 2 main areas. The top half is the application and their processes. In the application layer, we're talking about protocols like HTTP for web browsing, SMTP and IMAP for mail delivery, and FTP for file transfers. These applications create processes which listen on particular ports. That's the job of the transport layer, which uses the TCP and UDP protocols. We'll dig deeper into those very soon too. The bottom half focuses on getting the data from one host to the other. The network layer uses the Internet Protocol, or IP. You should be pretty familiar with this from the last 2 videos. The physical and data link layers move the data from device to device, that is, across switches, access points, routers, and other network equipment. Ethernet is a very common protocol here. And on this, we can see that the new version has broken the original link layer into the data link and physical layers. In the old days, there weren't very many different physical connection options. Now we have Ethernet, Wi-Fi, fiber optic cables, and so many more. While it originally did make a lot of sense to break up the physical connections from the data delivery, now we really have to. And that's why we now have 2 layers here instead of 1. Now into some more detail, starting at the top, the application layer. This layer defines the communications between applications on 2 hosts. This doesn't define how the applications work, of course. Instead, it describes on how the applications use the network. More examples here include SSH, Telnet, and RDP for remote administration. But we're just going to focus on HTTP as an example, because even if you don't know it, you're already familiar with it. We start with the applications. These are the web browser on the client side and the web server software on the server side. HTTP is the protocol that the applications use to communicate. If the browser wants to get a web page from the server, it will send an HTTP request. Just like OSI, the request passes down through the layers on one side and back up through the layers on the other side. Logically, one layer talks to the corresponding layer at the other side. The server will go through the same process to respond with the requested web page. The transport layer creates and maintains conversations between application processes on hosts. This is where TCP and UDP protocols come in. We haven't discussed these a whole lot yet, but put simply, they use port numbers to track sessions. Let's continue using HTTP as our example. The web server may have a process listening on port 80. When the client prepares its HTTP request, it will add a TCP header. We saw headers previously in the OSI video as well. The TCP header contains, among many other things, port 80 as the destination. It will also choose a port to send the request from. After the header has been added, we call this entire piece of data a segment. When the server responds, port 80 is now the source and the client's port is the destination. The combination of port numbers along with IP addresses enables systems to have more than one session open at a time and to track them. Without this, you couldn't have multiple tabs open in your browser, for example. There's a whole lot more to TCP, and we haven't even mentioned UDP yet, so we'll have a look at them in a bit more detail in the next video. Now, back to IP addresses. We've covered them along with routing and subnetting in detail in the last video. When the transport layer is done, the data is passed to the network layer where it is broken into packets, which are manageable chunks of data. We may end up with a single packet or many packets. It all depends on how much data there is to transfer. The point of this layer is to make sure that data from one host can find its way to another host. And to do that, an IP header containing the source and destination IPs is added to every packet. The path from one host to another may cross many networks. Packets need a router to pass from one network to another. That's why it's called routing. When the packets arrive, the host strips the IP headers off and reassembles the packets into the original data before it's passed back to the transport layer. Other network layer protocols you should be aware of are ICMP and ARP, but IP is enough for us right now, so we'll discuss the other two another time. Now it's time to quickly check that you've been following along. Let's say that you have two hosts on two different networks and they need to communicate. What device makes this possible? And as usual, the answers are on the website. The data link layer is responsible for delivery of traffic on a single network segment or LAN. In TCP IP terms, this means delivery within a single subnet. Common protocols here are Ethernet and point-to-point protocol. Ethernet is very common, so we'll use that as our example. An address, called a MAC address, is assigned to every device. Other protocols will use some form of addressing as well. To add these addresses, we add another header. In the case of Ethernet, a trailer is added as well. This entire piece of data is called a frame. If the two hosts are in the same subnet, then delivery is simple. One host just sends to another. But if they are in different subnets, we need a router. That means that the destination MAC will be the MAC of the router itself. When the frame reaches the router works out where it needs to send the packet by looking at the destination IP in the IP header. It then sets its own MAC as the source and the next device as the destination. If there are several routers in the path, the MAC addresses in the frame will be rewritten several times along the way. What are the names of each piece of data when they are encapsulated in TCP, IP, and Ethernet? The physical layer is exactly what the name suggests. It's responsible for physically transmitting and receiving data. There are many ways this can be done. Electrical, radio, and light signals are the options that come to mind. In any case, the data is encoded and the bits are transmitted over the medium. This will likely happen a few times along the path, like copper from workstation to a switch, fiber between switches, and copper through to the destination. Let's check now how much you've learned. How many headers and trailers will the original HTTP request be encapsulated in by the time it reaches the physical layer? What are the primary differences between the OSI and TCP IP models? What are common protocols that are used at the data link, network, and transport layers?
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.